Hi, my name is Shweta Anand, and this is my Lab 2 magnetic field of the bar magnet. Introduction. The purpose of this lab is to use a bar magnet and a magnetometer and determine the distance of a magnetic field. And so, some of the fundamental physics principles that we will be using is the Biot-Savart law, which I have written as shown right here. And then we also want to use the on axis formula and the perp axis formula, which I've written out here. Another thing to keep in mind is the magnitude of the magnetic field, which is distance dependent, as I've written here. And these formulas will be used for both our computational and our experimental model. For the preview of our results and also the procedure, I first used and calibrated a magnetometer and using a bar magnet, ruler, and tape, as seen in this image right here, and then I measured the magnetic field at different distances. This will be in our experimental model. I used that data to determine the distance dependence, and this was my physical experiment. Then I used my result and calculated a computational model using GlowScript and plugged in my formulas listed before, such as the Biot-Savart, on-axis, and perp-axis. I then use the results of that to compare to my experimental data. And so for a quick preview of my results, my experimental distance dependence was negative 3.5622 meters. The experimental magnetic dipole was 3.066, and then the magnitude of B at 45 degrees at distance D is 2.56589 e to the negative fifth, and that was determined with my computational model. So, some assumptions and observations that I made while doing this. So, assumptions that I made is that the Earth's magnetic field must be taken into consideration, and then also the bar magnet can be treated as a magnetic dipole. For our model itself, the system will be the magnetometer, which I used my phone for this, and then the surroundings would be the magnet and the Earth. Some observations I made is that when the magnetometer is far away from the magnet, it measures a near zero magnetic field in the x direction. As the magnetometer moves closer to the magnet, the measured x component of the magnetic field increases. This is my experimental data where I listed out my distances written here, and it gave me a plot of ln of bx versus ln of r, as you can see here. And my linear equation that I got from this plot will be used in the next slide, but this is overall a preview of my experimental data. So then here are my calculations to find the actual magnetic dipole. So I found R and N. R is the average of my distances, and N I got from my linear equation. And as I plug this in using the equations I've listed out below, I got a value of 3.066. Then I used this in my computational model where I did input my values, and I also um, wrote a formula to get my four arrows on a computational magnetic dipole, and that's written out here. And as this continues, you can see that this is the model that I got after I ran my code, where the blue arrow represents the perpendicular field, and the orange arrow represents the on-axis field, and then the purple arrow is this new arrow that I've calculated to get my magnetic dipole, but it's 45 degrees angle field. And as I ran this, I got a distance of 0.266339, and the magnitude was 2.56589 e to the negative 5. So, for discussions and comparisons, in my experimental data, I got a value of 5.2129 e to the negative 5, but in my computational data for the 45 degrees magnitude, I got 2.56589 e to the negative 5. So, the computational model and the experimental data are off, suggesting errors in my experimental process. Now, what could these errors be an indication of? The error could have come from other magnetic fields in the area, such as other technology, which could have altered the results, and also the calibration of the magnetometer may also be off. Questions for consideration. So, in this experiment, you oriented your setup to compensate for magnetic north. What if you hadn't done that and laid out your meter stick at some intermediate angle? Well, then the z component would not be affected, but the x and y would. We would be looking at different x components of Earth's magnetic field. Magnetic north contributes to both the x and y component, so it was different. So these would change. Also, if we had two identical magnets, but we redid the experiment and instead of using a single magnet, we used two identical magnets stuck together, then the measurements would be double in magnitude, but they would still be pointing in the same direction as our own experiment. It would be like replacing our bar magnet with a much stronger one. Thank you.